Hi students, welcome back. I hope you are doing good. So this is the last part regarding the properties of transition elements. So we will be discussing about some important properties like their color, their complex properties and their interstitial compounds formation properties. So why to waste our time? Let's start with this part. Formation of colored ions. So what happens in transition elements is that when an electron jumps from a lower energy d orbital to, and when that electron is excited to higher energy d orbital, that energy of excitation corresponds to the frequency of light absorbed. So you know that in transition elements they are vacant d orbitals, right? So if there is a vacant d orbital, now there are certain electrons which are present in inner orbitals. So if this low energy d orbital is excited to high energy d orbital, corresponding to this excitement, what happens is that there is certain energy related, that is nothing but the energy of excitation. So corresponding to this energy of excitation, there is a light which is observed. So this is an important point. So this frequency generally lies in the visible region. So this light which you are getting because of the excitation, this is lying in the visible region. So the color observed corresponds to the complementary color of the light observed. So the frequency of light observed is determined by the nature of the ligand. Now remember, ligands are also responsible for this excitation, right? So but the frequency of this light observed is actually depending on the nature of the ligand. So this is a very important point. So the frequency of light observed is determined by the nature of the ligand. So once you know the nature of ligand, your frequency of the light can be determined. So formation of colored ions. So here it is evident that zinc 2 plus, cadmium 2 plus, all the d orbitals are fully filled, and Ti 4 plus, all di orbitals are vacant. So once you have either fully filled orbitals or once you have vacant orbitals, there is no dd transition occurring. So therefore they do not absorb radiations, so they are colorless. So once we know that there is no dd transition, once there is no dd transition, what happens? It is a colorless. It is a colorless metal, right? So this is a very important. Next important point, formation of complex compounds. So this is a very again important property of your transition elements, that transition elements form complex compounds. So what are complex compounds? Complex compounds are of this nature. You have a metal, that metal is surrounded by certain ligands and there are n ligands. So this kind of nature, right, this kind of nature is called a complex. So metal ions binds a number of anions or neutral molecules. This X can be an anion like Cl minus or a neutral molecule like NH3. So it gives to the complexes like this. So you have these complexes FeCN6 3 minus, FeCN6 4 minus, CuNH3 4 2 plus and PtCl4 2 minus. And what is the reason of formation of complex compounds? Because this is due to the very important point again. This is due to the comparatively smaller size of the metal ions. So because of the comparatively smaller sizes of the metal ion, you can get the complex compounds. So the higher ionic charges and the availability of d orbitals for bond formation. So this is the first point. First point is this, comparatively smaller size of the metal ions, and this is the second point. The second point is the availability of d orbitals for bond formation. So these two important points actually comprises for the formation of complex compounds. Next, transition elements also forms interstitial compounds. So what happens is that when small items like hydrogen, carbon, nitrogen, they can be trapped sometimes in the crystal lattices of the metals. So once they are getting trapped, they become non-stoichiometry. You can see here, right? You can see here. You can see vanadium and hydrogen 0.56. What is this 0.56? This 0.56 is actually representing the non-stoichiometric component of hydrogen. So you can see here TiCMn4n Fe3H Ti hydrogen 1.7. Again this 1.7 is actually symbolizing this non-stoichiometric component of hydrogen present in this interstitial compound. So how interstitial compound is formed? Simple again, and small atoms like hydrogen, carbon and nitrogen that trap inside the crystal lattice of the metals, then your interstitial compound is formed. So what are the properties? Do the interstitial compounds have certain specific properties? Yes, interstitial compounds obviously have some specific properties, like they have very high melting points, higher than those of pure metals. They are very hard. Some boroids approach diamond in hardness. So for example, you have interstitial components of boroids. They have very high hardness and their hardness is nearly equal to the diamond, right? So this is a very important point. Next, the retain metallic conductivity. So once you have an interstitial compound of transition element, what is happening is that during conductivity they are retaining at any point of time. So they retain metallic conductivity and they are chemically inert. So interstitial compounds are chemically inert. What does that mean? It means that they are very less reactive, or they are behaving like your noble gases which are chemically inert. Alloy formation. Another important property of transition element is that they have the property of formation of alloys. So because of a similar radii and other characteristics of transition metals, they have the characteristics of alloy formation. So the alloys so formed are very hard and have often high melting points. So this is one of the first property of alloys. So ferrous alloys, so you can have chromium, vanadium, tungsten, molybdenum and manganese. These all are used for the production of variety of steels and stainless steel. So alloys of transition metals with non-transition metals as brass. So with brass, what is brass? Brass is formed because of copper and zinc, and bronze, which is formed because of copper and tin. So you can see alloys of transition metals and alloys of transition metals with alloys of transition metals with non-transition metal. You know that already zinc is not a transition element, even though it's d block element, right? So that's why here it is alloys of transition metals with non-transition metals. Catalytic activity. So another important property of the d block elements is that they have a catalytic property or catalytic activity. What is the reason of catalytic activity? You know that d block elements acts as a very good catalyst. Why? So you can see here the transition metals and their compounds are known for their catalytic activity. Why? Because this activity is ascribed because their ability to adopt multiple oxidation state to form complexes. So one of the important property of d block elements is that they have the ability to adopt multiple oxidation states. So once they have ability to adopt multiple oxidation states and they can form complexes, that's why they can use as a catalyst. So this is the reason why your transition elements actually acts as complexes. So you can see here iron actually catalyzes as 2I minus S2O8 2 minus gives rise to 2SO4 2 minus, plus in the process you are getting iodine. So the reaction between iodide and persulfate ions. So in all these reactions it is evident that how your d block elements can be used as a catalyst. Disproportionation. Another important property of your d block elements is disproportionation. So what happens is that when a particular oxidation state becomes less stable relative to the other oxidation states, one lower as well as one higher, it is said to undergo disproportionation. For example, you have manganese. So manganese actually becomes unstable relative to manganese 7 and manganese 4 in acidic solution. So what happens here? You can see here manganese 6. So this is manganese 6. So manganese 6 actually converts into manganese 7 and manganese 4. This is disproportionation. So I can also say that if the same element undergoes oxidation and reduction, this property is called disproportionation. This is the disproportionation. Right. So you can see here manganese, which is in +6 oxidation state, it actually oxidizes to +7 and reduces to +4. Right. So a particular oxidation state, which is now, this is less stable relative to the other oxidation states. So one lower and other higher. So this is the lower oxidation state, this is the higher oxidation state of manganese. So this unstable manganese actually converts into manganese of oxidation state 7 and manganese of oxidation state 4. So far students, we have discussed all the important properties of transition elements. So in this last part, we have discussed about their color, we have discussed about their tendency to form complex compounds, interstitial compounds, their catalytic property and their nature of disproportionation. So this is the end to the properties of your transition elements. In the next part, I will be starting with inner transition elements or F block elements. So till then, just stay tuned to our sessions. Goodbye, take care.